The room was quiet enough to hear the click of a counter and the scrape of metal on metal. A handful of people watched a practiced pair of hands hover over a small, dense sphere. They were there for a demonstration, a lesson that had been done before and done quickly. What they did not yet know was how much the next few seconds would matter. In the spring of 1946, Los Alamos was shifting from wartime urgency to peacetime procedure. The Manhattan Project had built and used 2 atomic bombs. A third plutonium core, completed but unused, became a laboratory object of study. Researchers needed to measure how materials behaved as they approached criticality, the point at which a nuclear chain reaction sustains itself. This required controlled experiments with real plutonium and real neutron reflectors, conducted in guarded rooms on a mesa in New Mexico. Louis Slotin had become one of the laboratory's most experienced hands. A Canadian-born physicist and chemist trained at the University of Manitoba and King's College London, he arrived at Los Alamos in 1944. He had become a hands-on member of the bomb physics team at Los Alamos and worked on assembling plutonium cores used in wartime tests. His calm demeanor and manual skill led him into a niche that combined physics with precise benchwork, assembling cores and reflectors, and performing criticality measurements for the bomb physics group. The plutonium core at the center of these experiments weighed about 6 kilograms. It was compact and highly radioactive. Wrapped around it, beryllium could act as a reflector, bouncing neutrons back into the core and driving it toward criticality. The safer method for testing this used spacers and remote handling. But hands-on methods existed as well, and in August 1945, one such experiment had already gone wrong. Physicist Harry Daghlian accidentally dropped a tungsten carbide brick onto a stack around a plutonium core and received a lethal dose. He died weeks later, in September 1945. The very same core would later be referred to by a grim nickname, coined after the fact, as stories circulated about the accidents that surrounded it. On May 21, 1946, shortly after 3 in the afternoon, Slotin arranged a demonstration for colleagues in a low, square building at Los Alamos. He placed the plutonium core on a stand and set one beryllium hemishell beneath it. He held a second shell above, lowering it until the 2 beryllium halves nearly enclosed the core. A neutron detector nearby clicked faster as the gap narrowed. Thin shims were the recommended method to keep the halves apart. Slotin, who had done this many times, used a flat blade screwdriver as a wedge to prevent the shells from fully meeting. The group ringed the table. Among them was Alvin C. Graves, a physicist who stood nearby and became seriously ill, but later recovered. Slotin talked as he worked. He guided the hemishell with one hand, maintaining a small gap with the screwdriver in the other. The detector readouts rose in step with the closing reflector. When the gap remained, the system was subcritical. If the gap closed entirely, the reflectors could drive the core into prompt criticality, a dangerous excursion. Seconds later, the blade slipped. The top shell dropped, the gap vanished, and the core became supercritical. Witnesses recalled a sudden blue flash and a wave of heat. Slotin reacted in an instant, flipping the beryllium hemisphere off with his bare hand to break the configuration. The neutron burst stopped almost as soon as it began. The prompt critical excursion was extremely brief, a fraction of a second, yet produced an intense burst of radiation. In the stunned silence after the flash, Slotin told the others to leave the room. He had them mark where they had been standing so that health physicists could estimate the doses they received. He reported a sour taste and nausea almost at once, classic early symptoms of radiation exposure. At the hospital in Los Alamos, doctors began supportive treatment. Over the following hours and days, he showed signs of acute radiation syndrome, vomiting, a sharp drop in white blood cell counts, and burns on the hand that had lifted the reflector. The doses to the others varied by distance and shielding. Graves, who stood nearest Slotin, became seriously ill, but would recover. Those farther away had lower exposures and were treated and released. Investigators reconstructed the sequence step by step. The apparatus was straightforward: a plutonium core that had been measured many times, and 2 beryllium hemishells designed to reflect neutrons. The purpose of the demonstration, was to show the behavior of the assembly as the reflectors approached a fully closed configuration. The accepted operational guidance called for shims to prevent contact and for remote instruments to move the parts. Slotin's practice of using a screwdriver to hold the gap was known but not formally authorized. The dose reconstruction, derived from detector records and position marks, placed his exposure at a level consistent with fatal whole-body irradiation. Within a few days, infection and organ damage became evident. On May 30th, 9 days after the incident, Louis Slotin died. The accident immediately prompted a pause in criticality tests at the laboratory. Norris Bradbury, who had succeeded J. Robert Oppenheimer as director of Los Alamos in late 1945, ordered a review of procedures. The core had been earmarked for post-war testing in the Pacific, but was not used at Bikini and was later melted down and recycled. Following the accident, Los Alamos reassigned materials and ensured that the Bikini tests proceeded with different assemblies. In the months that followed, Los Alamos formalized criticality procedures and increased health physics oversight. These events also prompted broader AEC attention and changes in criticality safety practices at other facilities. Experiments involving fissile materials near critical configurations moved behind thick shielding and into enclosures operated by remote controls. Neutron reflectors were assembled using mechanical stops and interlocks that prevented accidental closure. Training and oversight by health physicists increased. The laboratory also organized a dedicated criticality safety program, a model adopted at other facilities where uranium and plutonium were handled. For the people in the room on May 21st, the consequences varied. Graves recovered and continued in weapons research, later holding senior positions in the laboratory's weapons program. Others monitored their health for years, but no immediate fatalities beyond Slotin's occurred from this incident. Earlier, Daglian's death had already indicated the risks, and the second accident made those risks impossible to ignore. The incident became a turning point in laboratory practice. It occurred between war and peace, at a time when routine habits had not yet been replaced by standardized procedures. The rapid documented chain of events, assembly, slip, burst, response, provided a clear case study for regulators and engineers who designed safer systems. The core itself, destined first for war and then for tests, ended up as an ordinary part of the stockpile after melting and recasting. The changes instituted in 1946 remained, guiding criticality work throughout the nuclear age.